Hi everyone, my name is Dan Gibney, and today I'll be presenting our work on finding an optimal alphabet ordering to minimize or maximize the number of Lyndon factors of a string. Let me start by describing what Lyndon words are and what Lyndon factorization is. So a Lyndon word is a word that is lexicographically smallest among all of its cyclic shifts. So as an example, if our string is 00211, this string is lexicographically smaller than any of the strings you get from cycling the string around. So for example, 02110, 21100, etc. The smallest one is the one I first mentioned, 00211. So that's a Lyndon word. Now, a Lyndon factorization is a factorization of the string into Lyndon words, here labeled T1 up to TF, so that the Lyndon words themselves are lexicographically non-increasing. As an example here, if our string is the one listed here, it has 3 Lyndon factors, and this is assuming the usual ordering on the alphabet, which is 0 is less than 1 is less than 2. Now, let's talk about Lyndon factors, minimization and maximization. Why would this be important? Well, Lyndon factorization plays an important role in different string algorithms and in data compression. So for example, if we look at a transformation called the bijective Burrows-Wheeler transformation, or BBWT, this transformation is used in building indices and in performing pattern matching. And here, the construction of the index can actually be performed in parallel for the different Lyndon factors of that string. And more than that, if we want to do pattern matching on that index, well, the number of steps needed to locate the occurrence depends again on the number of Lyndon factors, this time in the pattern. And so that's just one example, but it shows that being able to control the number of factors within the Lyndon factorization of a string would have some value. And as such, this problem's been studied before. It's been studied before using heuristics like genetic algorithms to try to find alphabet orders that have nice properties in terms of the factorization. So the Lyndon factorization itself is actually unique, and we can prove it always exists for any string. It's unique depending on the alphabet order, but if we modify the alphabet order, we can get different Lyndon factorizations. And as a quick example here, if we take the string from earlier and we change the alphabet order to have 2 be less than 0 to be less than 1, then we get the factorization shown here. You get that there's 5 factors rather than the 3 factors we had earlier. And it's not increasing in terms of the lexicographical order between the factors. So what can we say about this problem of finding an alphabet ordering which minimizes or maximizes the number of factors? Well, first, we're going to show that the problem is NP-complete. So it's a hard problem. But more than that, we can show under the commonly used exponential time hypothesis that it can't be solved significantly faster than sigma factorial, where sigma is the size of the alphabet, or sigma is the alphabet. So specifically, you can't solve it in time poly t due to the little o sigma log sigma. And more than that, under the unique games conjecture, we can show that you can't even obtain a constant approximation algorithm for it that runs in polynomial time. So all these results are shown in our paper, and here we'll give an outline of how those results are arrived at. So let's give the main idea of how these reductions work. So what we're going to do is we're going to perform a reduction from a type of problem called Ordering Constraint Satisfaction Problem, abbreviated here OCSP. And I'll define briefly what these are, and we'll see an example. An OCSP of arity K is specified by a subset of SK, where SK is the symmetric group on K symbols. So lambda here is our subset. It's a subset of all the permutations on K elements. And that's the problem type. Now, an instance of one of these problems is actually given by a set of variables. Here we'll write V and the variables will be x1 up to xn. And also m constraints, where now each constraint itself is an ordered k-tuple of elements from V. And the objective is to find a global ordering on the elements of V, which will maximize the number of constraints satisfied. And by constraints satisfied, I mean that the permutation obtained by restricting the global ordering to the elements within each constraint is actually within lambda. So more formally, if we define a characteristic function, which is one if and only if the permutation is a lambda, and we consider sigma restricted to Ci as the ordering on the k elements of Ci induced by the global ordering sigma, we want to maximize this sum given here. Like I said before, we'll say that a constraint is satisfied if that permutation, when restricted to those elements, is within lambda. So that's a lot of formalism, but let's look at what a simple example of an OCSP is. A somewhat famous one is the Betweenness problem. So in this problem, k is 3, so it's of arity 3, and lambda consists of two permutations. The first one is the identity, or 1, 2, 3, and the second one reverses the elements, so 3, 2, 1. And what this means is for a given constraint, xi, xj, xk, it's satisfied if and only if xj is between xi and xk in the ordering. So these two possibilities here. And an example instance of the betweenness problem here would be the variables 1 through 5, so x1 up to x5, and the two constraints x1, x2, x5, and x4, x2, x5. If we consider this possible solution listed here, we can see that it satisfies the first constraint because x1 is here to the right of x2, and x5 is to the left of x2, so x2 is in the middle. But the second constraint is not satisfied as x2 is to the right of both x4 and x5. So the objective value here of this solution would be 1. Now let's consider a reduction from the betweenness problem to the problem we're talking about, Lyndon factor minimization first. To begin with, we're going to consider strings of the form T1 followed by x0 repeated alpha times, and then strings of this form, x1 gamma, x2 gamma, up to xn gamma, then that string repeated beta times. And the key point here is, by selecting alpha, gamma, and beta properly, we can ensure that x0 is going to be the smallest symbol in the ordering. And the reason we can do this is because if x0 was not the small symbol in the ordering, we would see that each of these would turn into at least two factors. So here, each of these beta substrings here would be split and create a new factor somewhere inside of them. And so to have an optimal solution, x0 would have to be the smallest symbol. And then using that x0 is the smallest symbol, our goal becomes to design T1 so that these different constraint gadgets, which I'll write as SCI for constraint gadget CI, have 3 factors if the global ordering on V is satisfied and 4 otherwise. And by global ordering on V, I mean the ordering that you obtain by taking the ordering on the corresponding symbols of T. Here's an example of a constraint gadget. Here, T is the index of the constraint, and you can see x0 here is repeated T times between each of these symbols. And the key point here is that there is exactly 2 permutations, which result in 3 factors, 3 Lyndon factors for this constraint gadget. And in both of these, it's the permutation on the symbols where xj is between xi and xk. So that happens here, and that happens here. All the remaining orderings result in 4 Lyndon factors being created. I can't quite remember if we found this one by hand, but it certainly is non-trivial to find this, this constraint gadget. But we like to do even more complicated ordering constraint satisfaction problems because it's been established that more complicated ordering constraint satisfaction problems lead to stronger hardness results. And that was established in these two works listed here. In particular, you have that if you have, in particular, one of the results is if you have an ordering constraint satisfaction problem of arity k, then for every epsilon, it's hard to find an approximation that gives you a cardinality of lambda over k factorial plus epsilon approximation, and that's NP hard under the unique games conjecture. So we'll see there's some other hardness results based on ETH, which we'll use, but the point is that we'd like to model more specific, more complicated OCSPs so that we can establish stronger hardness results. If we use the same form that we had from the last problem, now the question becomes, how do we find these SCIs so that the number of factors is controlled according to whether or not the ordering satisfies the problem? And so we look at this for a while and think, well, is there something clever that we can observe about the way that these factorizations happen that would let us design a really effective gadget for this problem? And for example, one thing we'd like to do is if you allow the arity to be between a certain number, like let's say 2 and 4, we'd like to be able to have constraint gadgets that evaluate the 3 factors, if and only if it's one of these permutations, and 4 otherwise. And so we thought about that a while. And at the end of the day, we found the most effective way was actually just to search for it. So we employed a computer program, and it just tried different permutations, creating different strings, and would perform the different permutations on the symbols and test their Lyndon factorization. And using about 2 days of computation, we were able to find some clause gadgets which did what we needed. And so here, the longest of these is of length 28, and that's not counting the lengths of the runs of x0 between the symbols. And what do we get when we look at how they get factored? Well, we get this table here. And with this table, we can see that you get 3 factors if and only if the ordering is the identity ordering. And so this is exactly what we were looking for. And you can imagine this took some computation to find. But after looking at it and reflecting on it a little while, I wasn't certain that this was actually could be discovered by hand. So I think in this case, the computer search was quite useful. Now let's look at maximization problems. And so for maximization problems, we need to use a slightly different form. Here, the form we'll use is this one here, where there's an initially increasing set of symbols here. Well, not necessarily increasing, but the set of symbols x0 up to xn in front of the string, and one final x0. And now, because it's a maximization problem, we want it so that if x0 is not the smallest symbol, there won't be enough factors being created. And that's what happens here. If x0 is not the smallest, then one of these other symbols will be. And what we'll find is there simply won't be enough factors being created within the other clause gadgets or constraint gadgets, which is what we're after. So now we need a good target ordering constraint problem to establish some hardness results. And one thing we can use, looking back at the theorem from earlier, is we can use the following OCSP. This one here, lambda, contains k-1 factorial different permutations. And these permutations are defined as all the permutations where the last variable is ordered first within the permutation. And now using from the result from earlier, we can say that it's hard to find an ordering that will satisfy more than m over k ratio of those constraints. So our clause gadget ends up looking something like this. So now you have this last string here, where the last variable appears being repeated alpha times. And so what happens is when this last symbol is ordered first, all of these alpha occurrences split into their own Linden factors. And so by setting alpha large enough, we're basically ensuring that that as many of those constraints are being satisfied as possible. Just to restate what we were able to do. So we were able to show that this Linden factor minimization and maximization problem is hard. NP hard according to exponential time hypothesis, and hard according to the unique games conjecture to approximate. And I think this problem also demonstrated the usefulness of using computer search to find gadgetry, especially when you have a very generic framework like that given by the OCSP. And so that's one thing highlighted here. And then the last thing is we were only able to find gadgets which would work for the exponential time hypothesis for the minimization problem to establish those hardness results. So we're leaving open whether or not we could find gadgets or a proof that would prove hardness for the maximization problem also. That's my presentation. Thank you for listening. Bye-bye.